If you could travel back 100 years with a modern laptop charger, it would weigh more than 2 kilograms and be the size of a small toaster oven. A full century just to shrink a plastic box. That seemingly trivial observation pulls us straight into the core of a conflict, longer than almost any technological war, the war of standardization. The charger, something we casually treat as an accessory, is in fact an unfinished contract between two eras, between the age of Edison and the age of Tesla, between direct current and alternating current, between mechanical machines and silicon mines. From the first incandescent light bulb to the modern smartphone, humanity's electrical infrastructure has never been redesigned from scratch. Instead, it has been patched, adapted, and forced forward until modern portable devices are compelled to carry a brick that translates the language of the old world. So why, after centuries of invention, have we still not escaped that box? The answer lies not in engineering, but in history. At the end of the 19th century, Edison and Tesla entered a confrontation that would define the future. Edison supported direct current DC stable, intuitive, but inefficient over long distances. Tesla, backed by Westinghouse, championed alternating current AC, chaotic in motion, but capable of traveling hundreds of kilometers thanks to transformers. The world chose Tesla. Global power grids were built on AC, a decision made at the macroscopic scale. But consumer devices, radios, transistors, computers operate on DC, at the microscopic scale. From that moment on, a permanent contradiction emerged. Every modern device must translate AC into DC simply to survive. The charger is the direct descendant of that conflict, a forced bridge between two physical philosophies. Tesla and Edison are long gone. But every time you plug in a charger, you are still voting for a decision made over 130 years ago. From the 1950s to the 1980s, the era of the linear adapter dominated. Large, heavy, and hot chargers built around iron cores and copper coils symbolized a time when mobility was barely imagined. The principle was simple. A transformer used magnetic flux to step AC voltage down from 220 volts to a few dozen volts. But to avoid magnetic saturation, the iron core had to be massive. Rectification and filtering circuits were secondary concerns. The result was low efficiency. Excess energy was burned off as heat. A nightlight left on overnight might feel warm, but a linear charger could burn your hand. In that era, electricity was still heavy. It required mass to exist. This physical limitation kept personal electronics anchored to desks. To make computers mobile, energy itself first had to become light. In the 1970s, semiconductor transistors and diodes opened a new possibility, controlling electricity with information, not iron. Humanity entered the age of the switched-mode power supply, SMPS. Instead of letting current flow continuously through an iron core, SMPS systems chop electricity into high-frequency pulses tens of thousands of times per second. Transformers operating at these frequencies can be the size of a finger, yet deliver substantial power. This shift did more than shrink chargers. It transformed energy philosophy itself. Energy could now be regulated by logic. Power transistors, from BJTs to MOSFETs, became energy valves controlled by digital signals. Control circuits continuously compare output voltage and command switches to turn on or off, maintaining stability. The charger evolved from a passive electrical component into a feedback-controlled system, a small brain balancing electron flow millisecond by millisecond. When consumer electronics exploded in the 1990s and 2000s, the world witnessed an explosion of black boxes. Each manufacturer used its own charger. Nokia at 5 volts, Sony at 8, 5 volts, Dell at 9 volts, Apple at 14 volts. Not only voltages differed, connectors did too. The energy world became a technical Tower of Babel. The root cause was not merely brand greed, but the absence of a global energy coordination authority. Power grids were standardized. consumer power was fragmented. Each company designed proprietary solutions to optimize batteries, performance, or simply to lock users into ecosystems. In 2014, the USB Implementers Forum introduced USB-C, a vision of a universal energy language, a single cable capable of carrying data, video, and up to 100 watts of power. Yet even USB-C failed to solve the problem entirely, a shared standard, but fragmented implementations. Some manufacturers added authentication chips to restrict compatibility. The war of standardization continues. With the arrival of new semiconductor materials like gallium nitride GaN, chargers entered the final stage of their evolution. GaN allows transistors to handle higher voltages and switch faster than silicon, reducing energy loss and heat. Power density increased dramatically within the same physical volume. At the same time, manufacturers began integrating power conversion directly into devices themselves. Phones, laptops. Even electric vehicles now contain internal energy conversion circuits. The external charger becomes merely an intermediary shell, and in the near future, it may disappear entirely, replaced by direct wall interfaces or contactless charging surfaces. This disappearance is not an ending, but the closure of a century-long loop from Edison and Tesla arguing whether electrons should flow straight or oscillate, to a moment when we have become skilled enough to make them do both on command. The charger, a relic of the old electrical world, is nearing the completion of its historical mission, translating the language of mechanical electricity for silicon.